Okay, so let's get started then. What I thought in doing a review, because we did a review for the second exam that included chapters 4, 5, and the first part of 6, then I'll probably focus my review on the newest part, which is the second and third parts of this last chapter. But if you read the syllabus, the exam will is comprehensive, but it will really cover material from pretty much the second half of the course, so chapters 4, 5, and 6. Probably with an emphasis on 5 and 6, which is the newest material. And 5, you recall, is the control volume approach. So I will. Oh no, it's on, but I have to send it to the screen here. Thank you. So again, it's focus on chapters 4, 5, and 6, but more so on 5 and 6. That doesn't mean ignore chapter 4. Chapter 4 is the one on kinematics. Chapter 5 is the one on the controlled volume approach. So that we covered in the second midterm, but it will come back in the final. And then chapter 6 is the long chapter that we broke up into 3 parts. So the first part, which was also in the second midterm, it's the same. I mean, it's a few things, but mostly stream function approach to problems in fluid mechanics. You know, but all the analysis of the formation, same material that you saw on the second midterm. So I'll just put here, etc. And then the 2 newest parts, which are potential flow and viscous flow. All right. So what I thought I would do is spend some time on this last chapter, unless anybody has a specific question about chapter 5. Maybe we can cover that first. Does anybody have a question about control volumes? Those are the problems where you treat the device, for example, or whatever the system is that has the fluid, and typically are problems where you're trying to find the force acting on that control volume. Yes.
Are we going to have chapter 1 to 3 at all?
You pretty much need to know that. Well, I would say chapter 2 is the one on hydrostatics. There won't be any specific questions about hydrostatics. Chapter 3 is the Bernoulli equation. So obviously you need to know the Bernoulli equation for quite a few of these problems. You have been using it. Chapter 1 is just an introduction. Any other questions about that first part of the course? Okay, so if we, and again, it'll be a longer exam because we have now 2 hours instead of just 50 minutes. So you can figure it'll probably be twice as long. Doesn't really mean that it'll have twice as many problems, but it'll be a longer exam. It will still have a portion on multiple choice questions, and then a few other problems, or problems that are broken down into parts. So you can at least get some credit if you do some of the parts, but not you don't do the whole thing. So let's recap a little bit. Maybe talk a little bit about potential flow. And remember, what we did is we first defined what a potential flow is. And what is a potential flow? What do we call a potential flow? A flow that is irrotational. Eh? So, irrotational flow. So the only requirement for a flow to be potential is that it be rotational, meaning that the curl of the velocity must be 0. And of course, the curl of the velocity is the vorticity. Right? So the vorticity, which is the curl of the velocity, must be 0. That's a potential flow. And then immediately from that concept comes the one that if a flow is indeed irrotational, then there must exist a function that we call the velocity potential, such that the velocity vector is equal to the gradient of that function. And that comes to us from mathematics because this is due to the fact that, let's just write here, since the curl of a gradient is identically 0. That comes to us from math. So that's what defines a potential flow for us. So that was the first part, definition of potential flow. And then, of course, if you are defining such a velocity potential, and this equation right here tells me what the velocity vector is, then, of course, I can find the components of this velocity, which are u in I, v in j, and w in k, as the components of the gradient. So u then would be the derivative of phi in x, v would be the derivative of phi in y, and w would be the derivative of phi in z. So the components of the gradient vector become the components of the velocity vector. And then we looked at the what we call the basic potential flows. So rather than rewriting the whole thing, I'm going to just summarize them because they appear here in this table. Is that visible for everybody? So this table essentially has the basic potential flows. So on the left-hand side, it tells you what the flow field is, and you will remember all of these because we have talked about all of these. Uniform flow, a source or a sink, a vortex, a line vortex, and a doublet. The doublet is considered one of the basic potential flows, even though it's actually made out of a combination of a source and a sink, as you recall. But it's treated as one of the basic potential flows. And then you have the expression for the velocity potential for each one of those 4 basic potential flows. And then, of course, because if we're looking at 2-dimensional flows, and remember that there is not a requirement that the flow be 2-dimensional. So if I put this back here for a second, never here in this definition of the potential have I said anything that the flow has to be 2-dimensional. The only requirement is that it has no vorticity. That defines a potential flow. But if I want to make use of both tools, the velocity potential function and the stream function, if I want to use both things together, then of course I need the requirements for the stream function, which are, what is the requirement for a, and let's just focus on constant density flows. So if the flow is already constant density, what do I need in order to use a stream function? It needs to be two-dimensional. So if I simply combine the two, I need the flow to be rotational so I can use the velocity potential, and I need the flow to be 2D so I can use the stream function. So if I want to use both, then I need both those conditions. And therefore, these basic flows are all two-dimensional flows. The uniform flow is a two-dimensional flow. So is the source or sink, the free vortex, and the doublet. And you can look at it on a plane and treat it that way.
And they all need constant density?
We're only looking at constant density flows, right? So you don't need to worry about variable density. You can have equivalent things with variable density flows, but we're not looking at those. We're only looking at constant density flows. But there is such a thing as a compressible vortex. You could have a vortex that has variable density. It's just more complicated. So for us, it's constant density. So therefore, I have a list then of my velocity potential and my stream function for each one of those four basic flows. And then you also have, which is nice, the velocity components. And you also have to keep in mind that only the first one is written in Cartesian, because the uniform flow, being a flow in only one direction, is obviously treated easily if you just have Cartesian. This one is actually, every time I worked out a problem here, I assumed that the uniform flow was from left to right. We just have uniform flow in all the examples. But it doesn't have to be. The uniform flow could be at any angle, as long as it is uniform. And therefore, what you have here is the general expression of the potential if the flow is at any angle. And they tell you here, angle alpha with the x-axis. So of course, if alpha is 0, then that's a horizontal flow. But if alpha is 90 degrees, then that's a vertical flow. But then the other three are much easily handled in cylindrical coordinates because of the way they are. Obviously, the source or sink is a flow, the flow is going radially out or radially in. The vortex, of course, is concentric circles for the streamlines, and the doublet is a combination of a source and a sink, and it's also more easily treated in cylindrical coordinates. That's why these are all in terms of r and theta. Right. Which means that you also need to know, I wrote this here, for the gradient, and you see it there, yeah. I wrote the gradient in Cartesian, but you also need to know the gradient in cylindrical coordinates. You don't need to memorize it because you can write it down on your equation page, but it's kind of tiny, so I'm going to zoom even more because they're even here at the bottom of the table. So right there at the very bottom of this table, you have the Cartesian components, u and v, in terms of derivatives of the potential phi or the stream function. Those are the ones that hopefully you have memorized just from using them. Those are easy to remember, but you know, these are newer to you perhaps and not as easy to remember, but they give you the components of the gradient, and of course we only need a 2D gradient. We don't need the third component. So it's the v sub r and the v sub theta in terms of derivatives of phi and psi with respect to r and theta. So those are the tools that allow you to find the velocity field, these expressions, the velocity field, if you know either the velocity potential or the stream function. And they're also the tools that you would use if you only know one of them. If you know the velocity potential, you can find the stream function, and vice versa. If you know the stream function, you can find the velocity potential, and that was a question on your second midterm. All right, so raise your hand if you have a question at any time, so I don't have to keep asking you. So after you master that, then we talked about the combinations. And I probably should shrink this again. So the combination flows are very important. You just take any two or more from that table and you put them together and see what happens. So we saw, what was the first combination that we saw? No, that was after. First we took uniform flow and a source or a sink from that table, and we put them together, and what did we get? For example, if we do uniform flow plus source, what will that give us? The so-called half body, right? So if I put the source here, yeah, that's my source, and I have my uniform flow from left to right, then if I combine those things, I find that there is a streamline. First of all, I find that there is a stagnation point here, right, when I look at the velocity. And then I find, so therefore there is a streamline that goes right through that stagnation point, with actually the velocity going this way on this side, because that's the source right there, going that way on this side, coming this way on this side from the uniform flow. And therefore there is a point there where they exactly match each other and cancel out, so you get the stagnation point there. But then we also find that if you follow the streamline that comes out of that stagnation point, it goes like that. Right? And of course I can put more streamlines. And then the next important concept is the fact that I can always take any streamline of my choice and think of it as if it were a surface. Because I don't have to satisfy no slip condition, because if I did, then I would start generating vorticity, and I cannot generate vorticity because then it wouldn't be a potential flow anymore. So I can say, well, I'm going to take this streamline and think of it as a surface. So if that is a surface, then that's how the half body is built. And then I just look at the rest of the streamlines that have to go, of course, around that object. So we did that. And you did a homework problem related to this when you combine the uniform flow with a sink, because you just get the opposite effect. And in fact, if I now add a sink, but I added somewhere back here, so this is the source, right? That's the source. But if I now come and put a sink here, in addition to that source, so now I have a source, a sink, and uniform flow, with the source and sink at different positions. Then, of course, what that does is it does the opposite on the back side, right? So you would find out that there is a stagnation point back here, and a second stagnation point, and then the problem just does the opposite in the back. So there'll be a streamline that goes right to that. This same streamline will go right into that stagnation point. Right? And if I just say, well, that is going to be the rest of the body, so I'm just, then we have this elongated object. Right? And then you can draw the rest of the streamlines. Again, this would have to, of course, go like that, and go like that, and go like that. So then you have a full body, which has a specific shape, because it has to be the shape of that closed streamline. So I think there was a homework problem where you only had a uniform flow plus a sink, right? If instead of doing uniform flow plus source, you do uniform flow plus sink, then of course it's like only doing the back of this, right? So if it's that, then if I draw the streamlines, so the source, the sink is here, the uniform flow comes from left to right again. Then, of course, I find a streamline that happens to end at a stagnation point here. And, of course, it comes from there, too. But now this is going the other direction, so it's going like that, like that. When it meets here, this is a sink, so this is drawing this way, but that's going that way. So it's exactly the opposite of the top one, of the source and uniform flow. It's just the back of this. And I think there was a homework problem where I think you were told, well, suppose that, there is a hole here. This is really something that is sucking the fluid. And then you were to find out, which fluid was going to be sucked in, or something like that. I forget. I think this all have to go there. The ones on the inside, which we don't draw here. But if we draw the inside streamlines, I'm sorry, they don't go, they have to go into the sink. They go there. They'll go right into the sink. So there was the problem that you had a sink that was sucking in the fluid. Let me do that a little nicer. So here's the sink. Here's the stagnation point. So there is one that goes, let me draw just the top side so I don't clutter it too much. Then all the other ones have to go into this sink. Even these ones will turn and go into the sink. Right? And of course, there is a portion of the fluid, if you're high enough above this special line, this is a streamline, but I'm going to draw it brown. It's not a surface. But of course, if you take a fluid element that is above that line, then that fluid doesn't get sucked into the sink. That manages to escape the sink. You remember that homework problem? Maybe, I don't know if it's in the very last set or the one before. Probably one before. All right. Now, no hands up. Okay. There could be other combinations, yes.
What would the body look like if the sink came before the source?
Oh, if you had the sink here and the source back there, but the flow is from left to right, you wouldn't get a closed, I don't think you would get a closed object. Okay. You wouldn't get a closed streamline. So uniform flow is still from left to right. There is a sink here and a source there. Yeah. I don't believe you get a closed streamline, but I would have to look into it. But yep. Yeah, again, the procedure would be find the stagnation points and see if there is a closed streamline that comes through that stagnation point. Another case is one where, for example, let me see if you can think about this one. Suppose I take, let me first draw the, well, actually I won't draw. Suppose I have a, two sources. All right. Suppose I take two sources. I put one source here, and I put another source here. But these are both sources. What happens? Let's analyze this one from scratch. So these are both sources. What do you think happens? First of all, can you say that there'll be a stagnation point somewhere? And the sources have the same strength, okay? So these sources, remember the strength of the source is defined by that M, right? So they have the same strength. Can you identify just from looking at that picture if there is a stagnation point? Where? Right in the middle, by symmetry. So I immediately know that there is a stagnation point here. Right? These are, remember, don't forget, these are both sources. All right? Okay, any possible stagnation points elsewhere that you can think of? You can start drawing the velocity. So what about this line? Do you think this line is a streamline? It has to be a streamline also because of the symmetry, right? So now you can put the direction of the flow because you know that since this is a source, it has to go that way, that way. This is also a source, so it has to go that way and that way. And of course, that confirms that there should be a stagnation point right in the center, in between the two. But now remember, what happens when you meet the streamline that comes from opposite directions meet at one point? What happens to the fluid? It has to go somewhere else. Right? So we know the fluid is going to have to go somewhere else. So, okay, let's see if we can think what that streamline looks like when it comes off that stagnation point. So it's analogous to what we were doing here, except that here we found that the streamline that went out of that stagnation point eventually has to bend. But what about in this case? Straight up. Like that, maybe. Will it bend? Can bend. So those are the things that you have to see just from thinking about the flow field. It couldn't bend because if it bends, it breaks the symmetry. And it has to be symmetric because there's two identical sources sitting across each other. So indeed, this streamline just keeps going straight up and down. So I could make that a wall. Right? So if I make this streamline a wall, right? Let's say that this is a wall. Because I can pick any streamline and make it a wall. So this is a wall. What kind of flow field do I have? Let's draw a few other streamlines. You will agree with me that they'll have to do like that. All right? So what is this? What would you call this field? And the same thing on the other side. What would be the name of this flow field? Name it. Huh? How about a source in front of a wall? That's what it is. Right? It's a source in front of a wall. Because I can completely, even though I know that the left side looks identical, since I have a wall there, this wall goes all the way to infinity. I don't really care what's going on over here. I can cross it out and look at only one side, and what I have is a source in front of a wall. So we generate the source, if you want to see the source in front of a wall, you just put a source on the other side, on the hidden side, and that does the trick for you. So you can see how these very elementary potential flows can be used to construct things that are a little bit more realistic, the more you build up on them. Suppose I ask you, yes?
So are the vertical streamlines, like after you get to 90 degrees, are they just going straight up, or are they also just moving away from the wall?
These ones that are bending? No, they'll have to get closer and closer to that wall, but without ever reaching it, right?
But just the ones that go vertically up from the source, what do they do?
My guess is that they probably won't because it's like you're squishing the float this like that. So I doubt this would go straight up. It probably has a little bit of a bend to it. But, you know, you could look into the details and see what happens. But it's more interesting to find out what's going on at this wall. More interesting to, now that you found that this represents a wall, then what's going on that wall? For example, could I find the pressure, the force that this flow field makes on this wall? Because I have a source and it's spraying against this wall. Could I find the force on the wall? How would I find the force on this wall? Huh? Well, that's only here. But what about higher up? What will happen to the pressure as I go up or down the wall? It's symmetric, so we can just focus on the top side.
Lower
Yes, why?
It's moving faster.
The fluid is moving. And remember, the one thing that we cannot do with these potential flows is satisfy no slip. So the flow has to slip past that wall. We can fix that later by learning other things, but not here. So the flow is just slipping by, and therefore, since now it has some velocity higher up, from Bernoulli's equation, the pressure will have to go down, right? So the pressure will drop. But will it drop continuously all the way to infinity? What's going on at infinity? Very far. If I know way up this wall, very far up.
Velocity becomes constant.
The velocity becomes constant? What is the velocity produced by a source? Just the source, by itself. As it goes away from the source, what happens to the velocity? It decreases. In what proportion? 1 over r. 1 over r, right? It decreases with r. So if I go very far, think of, for example, forget the wall, look at the back side. If I follow a streamline here and I go all the way far away, the velocity far away is going to be decreasing to 0. So if I go all the way to infinity, is 0. Well, the same thing will happen on the wall. So think about what's going on. The velocity is 0 at the stagnation point, then increases, but at some point it's going to have to decrease again, because it has to decrease all the way to 0 as I go very far away. So if I start thinking about what this pressure distribution might look like, if I do it with another color, it looks like, so this now represents the pressure. So it looks like there will be some high pressure here, right? But then that pressure will drop, right? Right? It will be less because the fluid is speeding up. But then the fluid at some point is going to probably reach a maximum velocity and start decreasing again. So it looks like this pressure will have to build up again, right, as I go far away. But of course, it's never going to, if this is the stagnation value, it will approach that, it will go in that direction, but without actually reaching it. So if I were to plot the pressure, the force per unit area, as a distributed force, it'll look something like that, right? And I can actually calculate what it is because I can find what the velocity is. I could find the velocity along the wall if I actually now look at the velocity and start seeing what the velocity will be. I'm not going to do the whole thing here, but let's think about how we would compute the velocity along this wall. So I'm going to redraw it here. What's the velocity, say, at some point here? Let's draw the source and the two sources again. Here's one source. Here's the other source. So source, source. What's the velocity on that blue dot? Why? 0, completely 0, but then that would be, now we have another stagnation point there. And we just agreed that it's 0 at the stagnation point and then it increases to then decrease again. But it's not 0. So how can I find the velocity there? Think about each source separately. Because remember, we use the principle of superposition. We can superpose what each source is doing separately. What's the velocity at the blue dot due to the source here on this side? Just forget the source on the left for a second. Just think of the source on the right. What's the velocity on the blue dot? A source just produces a radial flow out. So here, if I think of this line, I know the velocity will have to go that way because of that source, the source on the right. What about the source on the left? It'll be symmetric. So those two blue arrows represent the velocities due to each of the sources separately. But I'm superimposing them together, so what's the velocity going to be?
Straight up.
The sum of these two vectors, right? The sum of these two vectors. So it'll be, the sum of these two vectors will be something like that. We know it has to be straight up. When you said 0, you were thinking of the normal components. Because the normal components to the wall, those obviously cancel out because of the symmetry. But there is a velocity that goes up the wall. And we can actually calculate it, but I won't do it because I don't want to spend too much time. We only have about, 20 minutes left maybe? So, but that's the way you do these calculations. Another thing that I want you to be aware of is, and it has to do with this table, is that even though I have always put well, for the source and the sink, it doesn't matter because the source and the sink are symmetric. But I told you the uniform flow could have any direction. So suppose that I give you a couple of stream functions instead of velocity potential. We can do either one. So suppose that I say I have a stream function that is some number, say 5, times y. That's a stream function. What type of a flow is that? What flow is that? Uniform flow. That's uniform flow. This is uniform flow. In which direction? In the y direction?
X direction.
In the x direction. Why? Because the u velocity is this I dy. Right? And this I dy is 5. So this is a uniform flow with magnitude 5, whatever the units are, 5 units of velocity to the right, right? And v is 0. But suppose I give you another one, and I tell you psi equals some other number, 7x. What is that? This is still uniform flow. But now, in the y direction, up or down? So I know that u is this psi dy, that's 0. And v is minus this psi dx, and that's minus 7. So yeah, it's 7 units of velocity going down. So yeah, so you can have the uniform flow in any direction, and of course the combination at an angle is the one that I showed you in the table, at any angle. The only other one that you have to worry about direction of the 4 basic one is which one? Of these 4 that were on this table, the source and the vortex, there is no direction, right? Source is radially out, sink is radially in. But what about the doublet? The doublet has a direction associated with it because, remember, the doublet came from putting a source and a sink that were horizontal, and we put them in the center. And as a result, the doublet has an orientation to it. So if I put a doublet here, a gigantic doublet, so if I think of this doublet here, there is an orientation to it because it depends on where the source and sink came from. Right? So, because the way we did it, I think we had the source on the left and the sink on the right. So therefore, the orientation has to be like this. Because if the source came from the left and the sink came from the right, then when you put them together, they'll still have that orientation. And remember, if I draw the rest of the streamlines, then they were doing like this. Right? I just use those two so we don't get it too complicated, but there is an orientation to it. What does that represent? That doublet? A cylinder moving from right to left, right? From right to left. So when I added the uniform flow to this, in which direction did I add the uniform flow? I have to add it from left to right, otherwise I don't get the steady cylinder. Right? So if I take this doublet and I now add a uniform flow from left to right, that's how I get, when I do that, let's do it here. That's how I get the cylinder. All right. So I have to match the doublet with the direction of the uniform flow. I have to put them in opposite directions, otherwise I get something else. I don't get the cylinder. So how can I, suppose I want to do the opposite problem. I want the flow to be from right to left. What do I have to do to the doublet? I have to flip it. I have to flip the doublet. And here is the expression for the doublet. Right here. I'm working with stream function now instead of just to give you both sides of the story. So there is the stream function for a doublet. And that doublet was like the one I just drew. So if I want to flip it over, what do I have to do? If I want to flip this doublet, I change the sign positive, right? So I make the sign positive and now it's flipped. All right? What if I have the cylinder, no, what if I have the uniform flow, like I said here, in the second example, where it was coming down, right? So if I have the uniform flow going down like this, and I want to add the doublet so I can have the cylinder, how do I have to reorient my doublet? And my doublet, which is like that, right? And but I now have the uniform flow coming down. I have to flip this doublet. How do I change it?
Source on top.
Yeah, so the source would have to come from the top, which means that I'm rotating this doublet, right? Negative pi over 2. Very good. I'm rotating this doublet negative pi over 2. And how does that affect this, this stream function if I want to rotate it negative pi over 2? This is a little mathematical transformation, right? I have to change the theta to what? So this was their doublet, but I want to flip it around like that, 90 degrees, negative 90 degrees. What do I do with this angle theta? Plus, because I'm rotating, right? So the theta that appears in the sign has to be now, I'm rotating negative pi over 2, so it's this, right? In the doublet. This is the other part of the doublet, so let's write the whole thing. It was minus k over r. But now I have taken that doublet and I have flipped it 90 degrees. But what's the sign of theta plus pi over 2? Cosine with which sign? It keeps the sign, right? So this would be, this becomes minus k over r cosine theta. Because that's sine, it would be sine pi over 2 plus cosine theta, so the sign remains the same. So I mean the negative sign remains the same. Well, you can see that's also a doublet. So the sine, the doublet with sine theta is the horizontal doublet that we built the first time, but if I want the doublet to have another direction, it just becomes a cosine. all right? So these are manipulations that you can do to the basic potential flows to suit whatever situation you want to analyze, all right? Okay, no hands up. Let me talk a little bit about the viscous flows. And really, there isn't a whole lot that you need to understand other than the two flows that we looked at, the Poiseuille flow, so the flow, viscous flow, we went through the Navier-Stokes equation, we added the viscous term, but the only problems that we really looked at were the flow between plates, right? These are plates, or the flow inside a pipe. Those are the only two cases. And we did it with pressure. For the plates first, we did without pressure, just one plate moving. Then we added the pressure. For the cylinder, we just had a pressure flow. This is called Poiseuille flow. So there is an example, I think, it might be a homework problem again, where the problem is the following. Suppose I have an inclined wall at some angle theta, and I have a block. I have a block here that is sliding down. That's a typical problem you do in physics or in dynamics. Sometimes you do it with friction, sometimes you do it without friction. But the way we can do it in fluid mechanics, if we want to add friction, we can say, well, let's say that there is a film of some oil, whatever, that is here on the surface of this slide, right? And that film of oil is what produces the drag, what will slow it down, right? If I don't have the film and I have a very polished surface, then it might just freely slide down under gravity. Well, suppose that there is a film here, right, that has some thickness. It's a very thin film. And I'm told that it produces whatever necessary friction is needed to eventually bring this block, if this plane is very long, to a terminal velocity. Isn't there a problem like that you did, or you? I don't remember. Okay, so this block is now sliding at a constant velocity. And suppose that you're asked to find that velocity. Vt. Find the terminal velocity. What's the speed that this block is going to slide down? How do I do this? What do I do first? And we don't have a lot of time, so I'm not going to wait until you answer. So, first thing you do a free body diagram of your block. So there's my block. And then you put the forces that are acting on it. What forces are acting on this block? Its own weight, right? mg. And? No, it's just the friction due to the film. So there will be some force down here, right, which we can call the drag force, due to that film of oil on the surface. And if I am told that I am reaching terminal velocity, what does that mean? And of course, I can put the angle. The angle theta is this angle. Right? So which forces do I need to consider? In what direction is what I mean? In the direction, well, I don't know whether you have your x direction, but I was saying the direction of the plane, right? Of the actual plane. That's the one that I'm interested in. So parallel to the surface, right, the only two forces would be the drag has to exactly balance the component of the weight, right? The component of the weight. That's my force balance, right? Assuming that it's in equilibrium. So this is equilibrium. Okay. What is this drag force? Well, now I have to look at the film. So here's we have to zoom in under the block. So here's the block. And I'm zooming in. All right. What is the bottom of the block moving with? What velocity? What is the velocity here at the bottom of the block? It's the terminal velocity because that's the block velocity. So this is Vt. And what happens to the fluid velocity as I go into that film? It'll have to be 0 here because of no slip, right? So it has to look like this. Right? Hey, that's a co-ed flow. There's a co-ed flow under the block. Right? So, if this is co-ed flow under the block, what's the shear stress on the block? Viscosity times what? The strain rate. The strain rate. And what's the strain rate in this case? Vt over h. Okay. That's the shear stress. So, of course, what is the force? It'll be that tau times the bottom area of this block. Right? The bottom area of this block depends on the dimensions on the block, but let's just say area. The bottom area of the block. So if I put everything together, then what I have is that mu Vt over h times the bottom area of the block must be equal to mg sine theta. And I can solve for the terminal velocity. If I know the thickness of the film, right? If I know the thickness of the film and I know the property of the fluid, I can find the terminal velocity. Okay, so that's it. Study hard. See you Monday at 1:30. Thank you. Thank you.